Hello everyone, welcome back to introductory course on computational fluid dynamics. So today we are going to continue with our lecture series on computational fluid dynamics, and today's topic is derivation of continuity equation, which is one of the fundamental governing equations which we employ in CFD. So coming to the session outcomes, at the end of the session, student will be able to list out the assumptions and define the flow model which we are using to develop this continuity equation, and state the governing law on which we are developing the continuity equation, and try to establish a physical relation so that we can develop the mathematical model. Then we'll proceed with derivation of continuity equation and reduce the continuity equation to the specific scenarios such as steady flow and steady incompressible flow. So let's begin with the assumptions. The first assumption is that the fluid is assumed to be continuous. That means it is having a continuous medium, there are no discontinuities in the flow, and at the same time the fluid is assumed to be of single phase or uniform phase throughout the flow. That means there cannot be different types of phases of the flow or fluid. So it has to be either liquid or vapor, but it cannot be both. That means in certain cases there is transition of fluid from water stage to vapor stage. For example, in precipitation, these kind of activities, whatever phenomena is there, that we are trying to neglect here. By neglecting, we are considering that it is going to be a uniform flow such that the phase of the flow or the medium is single phase. Along with that, we are assuming flow to be continuous. Next, no viscous dissipations, so that there are no mass dissipation, mass losses because of viscous effects. Then we are considering electromagnetic forces to be negligible, which helps in avoiding or making the equation complex. Here we can consider even nuclear forces. So since it is the basic fundamental equation, we are considering these kind of forces to be negligible, so that we can simplify the cases. And next important assumption is no chemical reactions. So we have seen that whenever there is a chemical reaction, there might be change in phase of the fluid, or there might be change in the mass characteristics of the fluid. So we are trying to eliminate those and make our derivation a simple phenomena by considering there is no chemical reactions in the fluid. Next is flow model. So to derive this equation, we always need to have an appropriate flow model. So for the derivation of continuity equation, we are considering a control volume fixed in space, which is the basic flow model, and the Eulerian approach to develop the equation. So this is the control volume. We have already gone through the definition of control volume. So this is the control volume where the fluid is assumed to flow with a velocity v, and density of fluid is assumed to be rho, and it's represented by rho. So while deriving, we are assuming that the total surface area of this control volume is given by S, and the total volume is given by V. So these are certain notations we are considering here, and apart from this, we consider even surface area, elemental surface area we are considering as ds, and elemental volume which we are going to consider will be dV. So which we will be using in the representation of parameters. So while deriving, we will be considering small elements in the control volume and we will try to integrate over the complete control volume or surface area. So to conclude, we are using control volume fixed in space as the flow model, and we are considering Eulerian approach for developing or assigning the relation between properties of the fluid. Next is governing law. So to derive this equation, what is the basic governing law we are considering? So the governing law is law of conservation of mass. Law of conservation of mass states that mass can neither be created, cannot be created, nor destroyed. So the total mass of a conserved system is always constant. Whether there are changes in the phase of the mass, that is a solid might be transferred to gases or powder, but the total mass of the system has to be same. For example, if I take a paper and burn this paper, the weight of the paper burned should be equals to the ash weight plus weight of the smoke which is being released. So that is the conservation of mass. So total mass of the system is always going to be constant, and according to statement of law of conservation of mass, mass can neither be created not destroyed, but can be converted from one form to other form. So based upon this law, we are going to develop the continuity equation. This is a fundamental law on which the continuity is dependent. So since we are using this law, we need to have a physical relation to apply this law. So for that, we are considering the physical relation to be the rate at which the mass inside a volume is decreasing should be equals to rate at which mass is leaving the volume. For example, we consider a tank filled with water. This is a tank filled with water and it is connected to a tap here. A valve is connected here. So if I open this valve, the water starts flowing. So the mass of fluid leaving should be equals to mass which is decreasing inside tank. So this is the physical relation we are trying to apply for our continuity equation. So you can understand this with this small video. GIF is there. So we will be using that to understand what is exactly happening. So we will consider that. So you can see it's a two glasses are there. One glass we are pouring water to the another glass. So amount of water which is decreasing inside this container should be equals to amount of water which is being added to this second glass. So that is a concept we are applying to develop the continuity equation. So using this relation, we are trying to develop the flow model. Now let us begin with the derivation. Since we applied that law, let's try to apply it to the control volume. So we are considering control volume dV. There is elemental control volume out of the total volume. We are considering a small segment of the control volume, which I am representing it as dV. So based on this, the mass of this element dV can be written as mass is equals to density into volume. So using this relation, I can say mass of the element dV is equals to rho into volume of the element dV. So this is the volume and mass relation. We are using density or multiplying density with volume, we will get mass. Now according to the equation, we need the time rate change of mass. So for that, we will differentiate it with respect to time. So we will differentiate with respect to time. So what we are going to get is dou m by dou t is equals to dou by dou t of rho into dV, where V is the volume, rho is the density, and t is time. So time rate change of mass inside the volume can be written as dou by dou t of rho into dV. So if you see that glass, the volume inside the glass is reducing with respect to time. So if that is reducing, that means mass of the fluid is also reducing. Okay, since the volume is reducing, we can indicate it with a negative sign, and the total volume rate change can be written as, or decrease inside the volume can be written as minus dou by dou t of rho V with a triple integral. This is a volumetric integral. Volumetric integral of dou by dou t of rho into dV is nothing but the time rate change of mass inside the control volume. Now let us move to the next step, which is the rate of change of mass through surface. So we have seen that if water is flowing, that is happening through the surface of the tap. So the mass flowing through this tap is given by rho u into s, that is rho into velocity into s, which is time rate change of mass. Mass flow rate through surface. Mass flow rate through surface is given by rho into velocity of the fluid into area through which the flow is occurring. So for a small element ds, the mass flow rate through that ds can be written as dou m by dou t into rho u into ds. So for complete surface area, we can integrate it over the surface. So it is the surface integral. So surface integral of rho u ds indicates the rate of mass leaving through the surface. From equation 1, these two should be equal. That is, the mass which is leaving through the surface and the mass which is decreasing inside the volume, both should be same. So from equation 1, you can say that this is negative sign indicates that there is a decrease. Negative sign indicates that there is a decrease in the mass inside the volume, and the right hand side indicates the mass flowing through the surface. So this can be written as minus dou by dou t triple integral rho into dou v should be equals to rho u into dou s. So this will be the volumetric integral and this will be the surface integral. So this equation we call it as continuity equation in integral form, or sometimes you can rearrange the terms like dou by dou t of rho dou v with a triple integral or volumetric integral plus surface integral of rho u ds or dou s should be equals to 0. If we rearrange these terms, these are called continuity equation in integral form. It is valid for all the cases, whether the flow is steady, unsteady, compressible, incompressible. For all the scenarios, this equation is valid. So let us try to modify the equation for the required or the equation which is suitable for CFD. That is, as we already discussed, in CFD we always use partial differential equations which are to be solved using numerical methods. So to reduce this into partial differential equations, let us try to normalize the things. That is, the equation, continuity equation can now be written as volumetric integral. Sorry, this has to be a volumetric integral, and this is also a volumetrical integral, where we use divergence theorem to convert a surface integral to volumetric integral. So previously it was rho u ds with a surface integral. Now that can be written as volumetric integral of rho u into dv. So we are applying divergence theorem to rewrite the RHS of the previous equation and converting the surface integral into the volumetric integral. So the volumetrical integral term can be observed here, that is divergence of rho u into dv, where v is the volume. So the equation is now reduced to volumetric. So you can see that all the elements of the equations are now volumetric integrals. So you can rewrite the equation by removing the integral terms as dou rho by dou t plus divergence of rho u is equals to 0. This equation we call it as continuity equation in partial differential form. So now we have seen that we have developed continuity equation for in integral form. Now we have developed continuity equation in partial differential form. Now for specific cases, we have to reduce this equation to the required forms. That is, if flow is steady, then the terms which are partial differential with respect to time can be neglected, can be converted to 0. That is, in the previous equation it is dou rho by dou t, which is variable or which is being differentiated with respect to time. So we can reduce this to 0. So your equation will become divergence of rho u is equals to 0. Now for steady incompressible flow, since for incompressible flow density equals to constant, the density term can be brought out of the partial differential form. So your equation will further reduce to divergence of u equals to 0. So this is the reduced form of equation for steady incompressible flow. So the equations, both the equations represent continuity equation, but for a different or a specific condition. That is, the first one indicates for steady flow and the second one indicates for steady and incompressible. So to conclude with, we have seen that we have developed a continuity equation both in integral form as well as partial differential form using a control volume approach or control volume flow model, and we have reduced them to a specific scenario, that is for a specific steady flow we have reduced the continuity equation. At the same time, for steady incompressible flow we can write continuity equation directly now. So that's all for today. Thank you very much.